nicer once it's completed, you know.
Yeah. We'll start in another 1 minute. I think we have got sufficient quorum very fast, you know, because today I understand registered about 350 plus. Our limit is about 100. So balanced people will be on YouTube.
Hopefully Zoom will not crash.
Yeah. Because the project is the topic of the town, you know, so people are after that.
Yeah, it's been on the news, so I guess there is quite some attention to it. Yes, absolutely. Yeah.
Yes, we'll start. Good evening. Welcoming you all on behalf of Institute of Structural Engineers, Regional Group, Dubai. Myself, Sama Srinivas, Regional Chairman of the UAE region, and my colleague, Mr. Abdullah, Under Secretary of Regional Group. Today is being a special day for our Indian friends. Today is 72nd Republic Day for India. So wishing you all happy Republic Day for Indian friends. So to move forward for today's topic, which is very interesting. As you know, it's a topic of the town from last couple of months when it is lifted the bridge. So we have considered this topic quite a long time. We are thinking of this. Our speaker is available this slot, so we are able to arrange this topic this time. So this is our CPT talk, first topic, first talk of this year. Today's topic is about steel connections design at the Za'abeel One Link Bridge. And our speaker, Mr. Giovanni, is a double master degree from University of Cornell, New York, and Brescia from Italy. And he is leading matrix engineering from last 3 years. And he is with a focus on specialized steel structures for this region. Mr. Giovanni, this is the platform is yours. Please proceed.
Thank you. Thank you for the introduction and for the possibility to present this topic. I'll go through. I'll explain today substantially the methodology that we applied for the design of the joints of the connections of the main steel of the link bridge in the One Za'abeel development that is, as you mentioned earlier, Sama, is under construction now here in Dubai. I'll just go quickly through company's presentation just to give you an idea of who we are in Maface Engineering and what we do. This is the distribution of our offices all over the world, and including the office here in Dubai that follows the Middle East market, and our headquarters is located close to Venice in the north of Italy. These are some numbers of our staffs back, mostly concentrated in Italy and partially with representative persons in the other offices around the world. Some photos of our office and just an idea of what we do. We don't do only specialty structures. We work also in other types of engineering services related to mostly structural and facade services. Of course, the topic of today is closely linked to what we call special, especially of course with the steel elements, specialty structures. So I'll prepare something in my presentation related to what we refer to as one single model, which is our integrated approach for parametric design and I will show you later on a brief video of how this has been applied, how the one single model approach has been applied on these specific projects. So I just would like to give you some ideas about the project itself, and especially I would like to thank all the players that were involved in this project. Of course, our client that was had the most complicated part of the job. It was the fabrication and the erection of these horizontal tower, as it was defined, of the link bridge itself. That was Ithra Engineering. The main contractor, of course, Alec, that is executing a fantastic job. The consultant was WSP, together with Niken Sekai as the main consultant and architect. And the final client, of course, that was represented by Ithra Dubai and ICD, with Mace as project manager. I also would like to thank our team in Italy, led by Enrico Mazzarolo, especially with Marco, Riccardo, Jacopo, and Claudio, who have extensively worked on this project for a long time. The project for us was completed substantially last summer, after almost 2 years of design. The link bridge, going to more technical aspect, the link bridge is standing between the two main towers that you see also from the photos and from the render, at about 300 meter and 241 meter height. So the bridge is hanging at a height of more or less 125 meter from the ground level, and is 210 meter long. So you can understand, you can imagine also, as you've seen from the erection, it's a very, very heavy structure. And the design of the joints and the connections that had a weight of up to 45 tons was obviously one of the most challenging part of the project. For us, the joints were substantially identified in 3 typologies: the typical interface nodes, and the 2 joints in Tower A and Tower B, which we call the interface, so connected to the civil works in the main tower. Just to give you some numbers, we had about 1,000 joint secondary nodes connection that were, of course, analyzed in an analytical way. While between main and primary joints, we had about 520 number joints. The total number of typical joints that were then analyzed with the FEA approach that I will show you later on were about 190 numbers. So I just included some ideas about the assumptions or the design criteria that were followed during the design of these joints. First thing, the joints were identified in an optic, of course, of parametric design, were identified with zones, families, subfamilies, and then one unique number. Substantially, the zone were identifying the location of the joint. So, for example, upper chord, bottom chord, elevations on the Tower A or Tower B, and internal interface joint, and so on. Families were identifying joints that had basically same geometry within the same family, and subfamilies instead were identified joints that had the same profiles or same dimensions. The unique number instead was used to identify for every joint one single number that was not repeated anywhere else. Design-wise, the specifications were prescribing a high-strength material S460M and a specific product called High Star that will guarantee substantially constant yielding no matter what would be the thickness of the plates. And it was challenging in this project, and it was required because of the high thickness of the plates that were reaching up to 150 milli. And in terms of design, so the yielding at 450 MPa was then reduced of course, with the 10% by a 10% factor as per American AISC 360 10 regulations, and an additional 15% was applied to account for potential locking stresses effects. So at the end, the joints were analyzed with the nonlinear analysis, with the material that was considered elastic, perfectly plastic material, with the maximum yielding at 350 MPa compared to the 450 of the material performances, and with the maximum yielding that from the 5% that is typically prescribed by standards like Eurocodes was then considered up to a maximum limitation of 2%. For your information, all the joints were complete joint penetration. So of course, the connection design was then verified whenever the resistance of the base material was verified. And in terms of modeling approach, we used the Strand 7 as a software for the FEM analysis. In terms of numerical simulation, we had used in order to transfer the straining actions at for every element converging in a joint, we had used what we call the transfer beams, but were substantially moving the 6 components of the straining actions in every member up to the edge of the local model, where a rigid joint, the rigid links were basically connecting the straining actions to the plate. However, these being the transfer beams not connected in the center of the joint, there was a very small gap in between. The only way to guarantee the equilibrium would be that the sum of the total reaction of every component of the 6 components of the reactions will be equal to 0. And since this was not the case, because the global model was giving unbalanced reactions in the joint for various reasons related to the modeling, the global model of the bridge and of the tower plus the bridges, we decided to implement this technique that we've used in various projects, which is including also fictitious beam, which has the same center line as the transfer beam, but has a very low, substantially null stiffness. And in this way, the stiffness, the fictitious beam is able to balance the unbalanced reaction and distribute it between the elements based on the relative stiffness of the various converging elements. This procedure proved to be working, and I will show you later some of the results, and avoid any type of numerical errors during the FEA analysis. Some of the specific aspects that were analyzed during this project that are not really ordinary in the common structural engineering practice were the consideration for plate eccentricity. So substantially, we modeled the plates in order to take into account the additional moment generated by the eccentricity due to the fact that the plates are not aligned in terms of center line, which is what let's say the software will do automatically, and then also the effect of the cope holes on the localized stresses in the single plate, which you can see we had considered 40 mm on the safe side, 40 millimeter cope holes, and substantially the effects of these cope holes are substantially null. So this proved to be a verification that did not change the results of the design of the joint. So I would like to show you one typical then interface joint and one typical steel-to-steel intermediate joint. So we will start with the second one. This is, for example, a joint on the upper chord, family 1, subfamily 11, and in this case, the single node number is 4680. You can see the geometry of the elements of this specific joint. So we have plate thickness in this case from up to from 19 to 24 or 25 mm actually. The converging element section are represented on the left and then modeled correctly in the FEA model on the right. And the results of the distribution of the imbalanced reaction, in this specific case, for example, most of the combinations were giving reactions that you can see were in the order of 200 to 300 kilonewton. And we had also verified that with the design procedure with the fictitious beams that I explained you earlier, the increase in terms of stresses in the single elements and in the plates were amounting to basically few megapascals. So there was not really a big effect in terms of the design of the joints, but it was something that numerically we had to control. And then finally, the way the joints were verified were substantially checked in terms of Fomesis stresses on the left side with the limit of 350 MPa, as I explained you earlier, and of maximum then strain that, like we said, should be limited to 2%. In this specific case, the joint was substantially all in elastic regime, so there was literally no issue with the plastic behavior. Just to give you an idea of some of the complications, not only in the design, but also of the fabrications. Here, I've represented one of the joints with, for example, many converging elements. In this case, there's 11 converging members in one joint. So this was surely complex for us in terms of design, but mostly complex also in terms of fabrication for the contractor. And this is an idea of just one typical joint, how it could actually be fabricated step by step till the final, let's say, the final product. Moving to the interface joints, these are obviously the most critical connections in the whole project, and were basically represent the primary interface between the link bridge and the concrete towers. And they need to withstand the in-plane bracing forces that are transferred from the bridge to the concrete towers. On the bridge side, these reactions are totally taken by 100% taken by the steel sections. On the tower side, instead, the forces need to be progressively transferred to the RC works, to the concrete slab and the concrete wall. And in order to solve this type of joints, we decided to follow as well an FEA analysis, which I will show you. I will show you later in terms of results. But in a nutshell, we have adopted two types of resisting mechanism, and despite the standard would allow us to choose one of the two mechanisms, we decided to verify them both, which is of course an assumption that goes on the safe side due to the necessity of having a very robust design. So the first mechanism substantially relies on the bending strength of the column. So the bending moment is taken by the embedded column, so the vertical element, while the second mechanism instead relies on the bending and bearing strength of the horizontal steel beam on the again on bridge side. In terms of distribution, you can see in the top right, we had substantially 3 levels for every tower. So we had a total of 12 joints that were of 12 joints that were analyzed per tower and per level. Okay. So the 2 types of interface nodes that were identified were the purely interface nodes that I showed you earlier, that were identified substantially by embedded columns, beams, and diagonals, and what were called as K-bracing, that have this configuration with an embedded steel plate in order to redistribute the forces inside the concrete slab due to the bracing, in-plane bracing from the bridge. So graphically speaking, the transfer mechanism 1 that I explained you earlier is substantially the governing mechanism for the columns. So the contraflexor point, the full bending moment is given to the column itself, while the vertical and horizontal forces are distributed between the beam and the columns. And the contraflexor point was identified at mid-height of the column itself. And just to give you an idea of the amount of reactions that had to be transferred through these elements, we had about 70,000 kilonewton axial forces and more than 50,000 kilonewton meter bending moment. So very, very high reactions to be transferred inside the tower. The mechanism 2, instead, as I mentioned earlier, is relying on the distribution of the bending moment inside the embedded beams via a contribution of the bearing resistance concrete side. So in this case, the mechanism is usually governing the design of the embedded beam. In terms of the K-bracing, instead, what we did a similar, let's say, approach in terms of resisting mechanism. So mechanism 1 and mechanism 2, and again, these two mechanisms were enveloped in order to define a very robust design that will be able to withstand both the conditions. In terms of geometry, you can see these joints are really, really big. We're talking for one of these plates of about 5 meter dimension. And in terms of straining actions, you can see that we are taking the biggest, let's say, the most important component are the force Fx and the bending moment Mx, which are, let's say, in the box section, in the embedded box section parallel to the bridge, are substantially an axial force and the torsion. So these two components, you can see as per this table, amount to up to 65,000 kilonewton meter for the Fx component and almost 14,000, 65,000 kilonewton and almost 14,000 kilonewton meter for the Mx component. So the two mechanisms substantially distribute these two components in a different way. So in the mechanism 1, both the Fx, the shear force Fx, and the bending moment Mx are split with certain percentages between the concrete slab and the concrete wall. While in the second mechanism, the shear force Fx, so the 65,000 kilonewton, is 100% given to the vertical load, while the bending moment is still split between wall and slab. In order to define also the distribution of these components inside the main tower, we had agreed with the main consultant, with WSP, to define resisting mechanism factors that, of course, were different for the two mechanisms. So, for example, like we said, for the mechanism 2, the component Fx, so the main component of the shear force, is given 100% in the wall. So the factor is 1 in the wall and is 0 in the slab. And this is for every level, 26, 28, and 29. While in the mechanism 1, we said we will split it between the concrete slab and the wall. So we have 50% at level 26 between slab and wall, and 30 and 70% between the slab and wall at the levels 28 and 29. So substantially, these percentages were then applied to the straining actions in order to design and to verify the embedded section in terms of the straining actions that were coming from the bridge. So this is basically how the transfer mechanism were then verified. Of course, we took into account the existing bars and the Fx and Fy components are taken by substantially by a strut and tie mechanism. So with, of course, compression on concrete side and tension on the rebar side. And similarly, we did for the two moments MX and MY that are transferred inside the slab. So also in this case, compression in the concrete side and tension in the rebars. And then similarly, we did the similar distribution for the wall. And of course, the extensive shear studs that were present were then defined studs, and the rebars were designed based on the straining actions distribution and the percentage of the resisting mechanism that I showed you earlier. So FXFZ and MX and Y for the wall. So the results then in terms of, this was more, let's say, an analytical approach. The joint was, of course, also designed in terms of FEA analysis to verify the stresses in the plates and in the converging elements. And these are the results of one typical interface joint in terms of stresses and strain. And similarly, we did then for the K-bracing. So these are the results of the stresses in all the converging elements, in the wedge plates and in the stiffening plate inside the box beam. I have a quick video that I would like to show you in terms of how then the parametric approach was used for this specific project. So how the process of designing these joints and verifying these joints that, like we said, are in very, very big numbers was made as automatic as possible. So we started with the definition of the IFC geometry that was imported, in this case, into an IFC file, where all the elements, all the plates of the joints and the converging elements in the joint itself are identified in terms of their dimensions and materials, and in this case it's all S460. Then we imported the global model. We had two models from the basically from WSP for the main bridge. There was an ETABS and the SAP model. So these models were then imported in terms of all their information, so geometry and straining actions, inside the Grasshopper platform. And basically the nodes were imported in terms of coordinates from the Excel file. And then we imported the connectivity of all the beams. And once reached that, then we could switch on in Rhino to visualize all the elements, as well as so all the elements here, you can see that they are already defined in terms of all their properties. And of course, with the unique number that corresponds to the SAP and the ETABS model. And then we did the same for the joints, which will come shortly. So for the joint geometry, we did the same to import it inside the wireframe. So if we switch on the related layer in Rhino, we're able to visualize actually graphically each one of these joints. So like I said, all the plates are correctly modeled already, and they are already imported directly from Grasshopper. If we select single plate, all the properties of these plates are already assigned. Substantially, in this case, it's the thickness, so the dimension of the plate and the thickness itself. And then the next step is the generation of the FEM node by Grasshopper. So we input the wireframe, we input the ETABS, we process the ETABS wireframe. We do the same with all the beam properties. We do the same for the SAP global model, as well as the beam properties as well from the SAP. And then finally, we're able to import, to process all the forces, all the straining actions for every element. This is the input that we had. So the 6 components of the straining actions for every converging element in every joint for every combination. and then we select which type of joint we want to analyze with the single joint number, family, subfamily that I described you earlier. And then from the console, we're able to create to mesh the surface, which you can see here on the left side. So the surface is automatically meshed already in Grasshopper Rhino, and it's ready then to be exported. And we can then save the FEA model, which creates then in the next step a TXT file inside an automatically generated folder with the unique number of the specific joint that we selected. This is all created automatically. Then we can import the TXT in our solver, which is Strand 7, and we can cross-check that all the elements, all the plates are imported correctly in terms of their geometry, their thickness. And so the geometry is substantially correct. We can check the plates also in terms of their thickness, if it's correctly matching with the IFC. And then we have a cross check on the like we said on the transfer and the fictitious beams that I explained you earlier, that allow us to transfer the straining actions for the transfer beam and to avoid numerical errors for unbalanced reactions. And then finally, we check all the straining actions for every combination for all the for both the models, etaps and STAP, that are automatically imported already inside Strand 7 via Grasshopper. So substantially, the model is ready then to be run, and nonlinear analysis basically started, and then the results of these nonlinear analysis are what I've shown you before in terms of stresses and strain distribution. Another interesting topic in terms of automatization for us was the necessity of updating this simulation with what was called the validation approach. Just before basically the lifting of the bridge, there was the necessity to recheck joints due to some modifications in the global design. So the way this procedure was done, again, in the same platform in Grasshopper, we added a tool also to automatize the process of the reporting generation. So basically, in this way, we were able to update all the reports that were generated previously, of course, in a manual way, automatically. And this would have taken much longer if done it in a standard way, let's say, and allow us to avoid any type of delays then on the site activities. So what we did, we substantially in Grasshopper, we created a fold path where all the FEA nodes needed to be analyzed. We created a log file path, and we defined where to save then the analyzed FEA joints, and we decided how many. We could decide also how many nodes to be run simultaneously. Then in the next step, once the joints were analyzed, we were able to list the nodes that we wanted to report simultaneously. For example, in this case, there's a list of 13 joints, and we had the path defined for the saving and updating actually then the report. So the outcome of this activity was basically the update of the report that you see here on the right, where all the pictures that were needed to be replaced with the new results of the new simulation were automatically updated. So we had a total, just for the main FEA joints between interface and typical joints, we had a total of 14 number reports, and we were each one of these reports had an average of 100 to 150 pages. So we were able to update all these reports in the quickest and most automatic way. And then the results of the stresses and strain that you see in the top and the bottom part were automatically then updated. And these are some photos from the site just to show you some the dimension of some of these main joints, and then some of the stages of the installation. These are some of the embedded elements with the shear studs, and then the bridge, as you probably seen, was then lifted substantially in one piece, with the exception of the last 900 tons of the most cantilever part, and lifted in position in one stage. I've completed from my side, Sama.
Oh, that's good. So the connections are big. The topic is good, you know.
Yeah, nice. They are very big. Yes.
We have some questions. We'll take up some now.
Yeah, sure.
The first question is from Mr. Khaldun Almafsha. Have you considered earthquake movement in connection design, if based on static or RSC approach?
Pardon, could you repeat the question?
Basically, did you consider earthquake movement in connection design? Did you consider earthquake movement in connection design?
Sorry, Sam, I didn't hear which moment.
Earthquake movement.
Earthquake moment, yes, of course. Yeah. All the load combinations that I showed you, these massive Excel files that were coming from the main design. The main design were an SAP and an ETAPS model developed by WSP, and WSP, of course, have considered all the load cases, including earthquake. So the straining actions that were then imported were, let's say, we were using all the combinations, including earthquake, wind, and all the cases.
Good. There's a question from Mr. Sabi Kisaf. How did you design for differential settlement between the two towers?
This is something that is.
Sorry.
Yes.
Question a little bigger again. Again, the temperature, because as you know, the length of the bridges you mentioned bigger. So how you consider temperature in the design of the connection?
Yeah. To answer the second question, the temperature effect was considered in the global design, and the straining actions related to the temperature effect were part of the input that was used in the connection design. To answer the first question instead, this is something that is related to the global model, which was defined by WSP, and of course the effects of the settlement on the two towers were considered. What I can say from our end in terms of the topic that we were studying is that we had considered additional, let's say, tolerances for the installation of the bridge. And in terms of modeling and straining actions, we had considered an additional component of the bending moments due to these additional eccentricity. But the effect of the settlement, the differential settlement between the two towers are taken directly inside the global model. It's not part of the specific of the connection design. But for sure, it's part of the global model. The two towers are embedded inside the two. The bridge is embedded inside the two towers. It's transferring bending moment on both sides. So it's not simply a supported element.
Basically, it's an integrated bridge.
Yes, in both sides.
What is the governing load in connection design?
There were various conditions. One of the, for sure, there was wind was one of the governing combinations, and especially those 50 plus thousand kilonewton meter that I was referring to was coming from load combination, from wind load combinations. Yes.
I think again the same question, maybe in a different way. Have you considered long-term differential axial shortening of towers against a global model?
Yes, I guess it's yeah. It is. This is. I mean, I unfortunately I cannot answer because this is something that it's a question that should be reverted to WSP. But for sure, long-term settlement were considered.
Actually, what is intention is if you have two towers, the load is different. If one of the support sinks, how that it's a bridge is designed according to the differential settlement? You don't have any idea.
The scope of our design was the design of the connections. So the straining actions that are imported inside the connection design are already accounted for differential settlement. So it's something that is already embedded inside the straining actions that are imported in the model from the global model.
Yeah, question from Mr. Munir Matha. So your question is very big. I just brief you. So being the biggest plates and the tubes, how the reinforcement conflict is managed? Because we got a reinforcement, we got a plate. So in embedded corrections, how you managed?
Well, it's indeed very dense, as you've seen for some of the pictures. However, there was the necessity of having this type of embeds. So, of course, one of the solutions was using high diameter rebars. Okay, the rebars are grade 400, so it's a standard B400 grade. But substantially, there was no specific requirements other than that on the concrete side. So, of course, they are extremely dense elements. So we were trying to use the existing bars as much as possible, but I guess you could see from some of the models as well as the pictures that we had high density of reinforcement embedded, especially in the slab and in the column, because of the very high value of especially of the shear force and the bending moment that we had to transfer to the bridge itself.
Okay. A question from Mr. Richard Tharun. How are the deflections of the link structure has been considered in the design?
The deflection of
the link structure has been considered in the design. Again, it's the same question, I believe. Everybody is talking about overall deflection.
The differential settlement, yeah. Yeah, I guess that's related to the differential settlement. So the only thing I could show you on that topic is that we had considered, like I mentioned before, the effect of the geometrical imperfection from the bridge side. So we had considered plus minus 50 milli. And because, of course, during the installation, the final geometry could not be guaranteed 100% from the bridge side, and this will transfer additional bending moment from the bridge to the tower. But this is not really related to the settlement; it's related to the installation tolerances of the bridge itself.
Good. A question from Mr. Nabil Athari. How did the temperature variations between dealt within the design stage and erection stage?
The temperature variation, sorry?
Temperature variations during the design stage, meaning design stage means what his intention is for overall serviceability stage, and during erection stage. There are two stages.
The erection, although again, the erection design was developed by the steel fabricator, by Versendine, not by us, but the erection was carried out over the night hours, so that there would be a control on the temperature variation. Design-wise, the temperature variation effect was considered already in the global design. Absolutely.
A question from Anonymous. What was breakout of concrete? Basically how the bonding strength is calculated between the concrete and steel, and what grade of concrete they used?
The concrete was grade C80. Okay, or C85 actually. And what was the other question? Sorry.
How the transfer of breakout, basically the bonding strength between the steel and concrete, how you are make sure that it's working well?
It's via shear studs. So let's say the embedded part is working naturally, and I could show you the way it was modeled substantially was via springs. So substantially modeling wise, we had considered a certain spring value from the concrete C7085, and the way this was then guaranteed in terms of transmission of forces within the section. For example, for the embedded for an embedded element, the transfer of the axial forces was via shear stud, let's say, surrounding the section of the element. In this case, it's either a box section or a built-up open section, I section. And in the same way, we did transfer the bending moment in either the weak or the strong direction, where again there is a composition of compression tension, and the relevant then shear stresses in the studs are designed in order to take these reactions.
Okay, good. There's a question from Mr. Payam Ismaili. How was the third-party design check and approval process taken place?
Well, there was a third-party approval on job by municipality, and they had reviewed every single calculation report model. Even in discussion with the third party, we did separate model with other software, just to to give the required level of confidence. So the design was a third party reviewed and stamped and then approved by Dubai municipality.
Okay. Question from Mr. Kalam. I think he is also a very good technologist in structural engineering. There are many questions from him, from his side. What were the first steps you did to define the connection geometry?
The first test?
What are the first steps? Did you define the connection?
Well, I mean, I started from the numerical results, but substantially these joints were conceptually defined by WSP. Okay, so as part of the tender package, what was given to the fabricator, the joints were already identified in terms of their main geometry, and the purpose of the steel fabricator was partially the verification of these joints and partially the modifications whenever required. For example, with additional plates, increasing in the thickness of certain plates. The only elements that were, I would say, had to be completely designed from scratch, okay, or sketched from scratch, were the interface joints, especially the K-bracing. So for the K-bracing, with the mechanism that I showed you with this wedge plate, it's something that we had defined, considering the magnitude of the forces, considering the geometry of the slab and the wall. So there was a significant change for this design compared to what was in the tender. But the main joint, the main typical steel-to-steel joints were, in terms of their general geometry definition, were already defined in the tender.
Oh.
And anyways, the plates of the joints are always as thick or higher than the converging element, and we have complete joint penetration everywhere imposed by the specifications.
Then same process. What did you do if you needed to update the geometry based on the stand 7 analysis? If you got any evidence, what do you do? What did you do?
Well, this was done in Grasshopper automatically. So let's say that, for example, if we take one of the typical joints, let's take one of them. So, for example, for these joints, in case the plates, one of the converging plates element would need to be modified. For example, we could take this example from the original thickness to a higher thickness. The advantage of the automated process is that if, for example, all the stiffening plates inside these joints, which are 75 mm thickness, will need to be increased for certain reason to 80 mm. This could be easily done and in the most automatic way inside the Grasshopper itself, okay, because the geometry of the node is defined in there, and this will automatically update with the baking process the TXT file that is then imported in Strand for the analysis.
Okay.
So the operation, let's say, is not done directly via the solver. It's done fully under the Grasshopper platform.
Again, question about integrity only. See, everybody asking about differential movement between the two towers. Basically, how you estimate future settlements. You know, how you I know it's an integrated bridge. Is part of your scope or
no, it's part of main design.
Okay, we take a couple of questions. Okay, again, what is the maximum forecast or estimate future settlement once the link bridge is in long term? I think this also.
I guess I guess all questions unfortunately related to the settlement or the global design of the towers. I don't think it's something that I could answer possibly.
Yeah. Okay, what are your major challenges to convince authorities and your clients in your project?
Well, many challenges. I just show you a few of them from the usage of the software. We selected Strand 7 for specific reasons because we knew that with other commercial softwares we wouldn't be able to depict, for example, just to give you an idea, over 150 milli thickness plate. We wouldn't be able to check the variation in the stresses within the thickness of the plate. In other commercial software, this is not possible. And another challenge was, well, I showed you a few examples related to the eccentricity of the plates and the modeling of the couples. This is something that we didn't, let's say, initiate by our side. It was requested to us. Other challenges for sure were related to the fact that the automated process is not maybe cannot be fully controlled by others, so it was challenging to show and explain how this was actually done. And fortunately, we had the chance to meet with the municipality and explain them. So and definitely the embedded joints, it was a good decision for the interface joint to design for this double mechanism that I explained you analytically, considering both the mechanism, because this was one of the things that was requested, for example, by the municipality later on. So if we hadn't done that, we could have reached a design that maybe would not pass the approval of the municipality.
Oh, okay. And what is the grade of steel? Any special grade of steel used for the connections, or it's the same?
That, as I mentioned earlier, the grade was imposed as standard as grade S460 that was used for all the hot rolled sections as well as for the plates. Of course, for the secondary, the other commercial secondary profile, there was grade S355. So a standard grade S355. And the peculiarity of these S460 were two, I would say. One, the high star, so with the constant yielding, no matter what will be the thickness of the plate. And this would be very important because with such thick plates, then we would have otherwise a significant reduction of the yielding itself. And the other characteristics was the Z quality. There were quite high requirements of Z quality. For most of these plates, especially the thick plates, we had to verify them for Z35 quality for the through thickness. I could say another aspect related to this material was the challenge related to the toughness of the material itself. And I think there was maybe a note that I had included related to that I could show you. Yes, this one. So for the S460M, what we did, again, this is also something that followed discussions between the consultant, the third party, the municipality. Altogether, we had decided then to check the performances of this high-grade steel with considering a reference temperature of 15 degrees and the stress of 60% of the maximum yielding. Okay. Of the maximum von Mises stress that will come out of the FEA analysis. So as a first step, what we did, we check some typical joints. We extracted the maximum stresses that were around 350 MPa. That was the limit that was set for the yielding, as I explained earlier. So 60% of that was 210 MPa, and substantially then, as per Eurocode 3, we had identified then that the maximum allowable thickness will be 130 milli as per this table. So this table would basically tell us that considering ULS stresses of 350 MPa, the maximum thickness is 130 mm. Above so up to 130 mm, basically the toughness requirements for S460 are directly verified without any specific assessment. For plates above 130 mm, as I mentioned, we had some plates arriving up to 150. The maximum stress, as per again as per Eurocode, would be around 300 MPa. Okay, 43% of the yielding. So what we did then later on is that for all the plates between 130 and 150 mm, we verified that the stresses will not be above 300 megapascal. And this is one example of one of these joints. So for example, these box section has plates of 150 milli thickness. So in order to verify the toughness requirement, we check the stresses, and we identified that except for very localized peaks areas, most of the surface of the plate elements are experiencing a stress which is lower than 300 MPa. So again, then the toughness requirement for the S460 M grade are verified. And from here, you can probably appreciate what I was mentioning earlier related to the necessity of verifying the variation of the stresses over the plate thickness. So you can see that in the external surface of the plate thickness of 150, we have much higher stress than what you would experience in the internal surface. And this is something that with other commercial software you may not be able to capture, let's say.
Oh, okay. Good explanation, Giovanni. There's a question from Mr. Manoj. It's a good question, I think, I believe. How did you validate the algorithm followed in Reno and Grasshopper with respect to manual calculations?
Sorry, how did you
validate that your design is right from your analysis?
Well, manually, let's say most of out of the 1,000 secondary joints that I was mentioning you in terms of numbers in here. So the 1,000 secondary joints were designed with the analytical approach. Okay, so with basically with spreadsheet and analytical calculation. There was no FEA analysis. The only joints that were analyzed with the FEA as typical joints were 190. Okay. So we had 190 typologies. For these joints, there was no possibility to do an analytical assessment, simply because the geometry of the joint, the thickness of the converging elements, the size and the number of converging elements is not simple enough to use analytical approaches. Or better, it could be used, but it might lead to results that will not be that close or may not capture some of the aspects that you could capture with the FEA. So analytically wise, if you had to verify these joints, for sure they would be verified, especially considering the fact that I was mentioning that the thickness of the plates is always higher than the thickness of the converging member. But this there would be the risk eventually to underestimate certain aspects that instead with the FEA analysis you would be better captured. So this was the decision. There was not a clear validation, but the validation of the main FEA joint, the biggest one that I showed you, that we did with this procedure was already, let's say, automatically done.
Okay. one more thing, will you able to share your email ID or contact details? I can see a lot of questions, but mainly towards general building behavior and how reflections and etc.
Yeah, unfortunately for that, I would have to transfer the questions to our colleagues of WSP who were designing the main bridge. Yeah.
Okay, good. We'll see the possibility of contacting other persons. So I request all the members not to post questions on general behavior of the structure, global behavior. You can post a questions related to the connection design. That will be helpful so that Mr. Giovanni can help you or assist you. Yeah. Last question. Is it, did you consider fatigue design in the process, in the connection design?
No, there was no specific requirements for fatigue design.
Okay, good. I think we are coming to the end of the session now. Good. So coming to our institution activities, as you know, this year also we are proceeding with all the online webinars and CPD talks. On an average, we plan to do a monthly one talk minimum. That's what our aim with circumstances given. For the quite a few of people new now, being an online session, we are reaching to the wider audience. As you know, people who don't know about ISTRUCT, we are a platform of Institute called Institute of Structural Engineers. We are about 28,000 practicing structural engineers, a part of this institution. ISTRUCT in a short form, it works on structural engineering practice and profession to support in preparing standards, guiding structural engineers across the globe. And we offer various memberships, graduate members and chartered members and fellow. There are procedures available. Please go through our website, www.istruct.org. If you need any information related to the membership, please contact me or directly from the website, any email ID, what you get a membership section. That's all from my side. And thanks to Mr. Giovanni for your great explanation about connections for that great bridge. We believe we'll see the whole bridge to be completed. We'll have to see there, going there, and maybe there's a swimming pool. If I remember correct, there's a swimming pool in the same bridge. I understand?
Yeah, that's correct. Yeah.
Okay, good. So there's many questions are going to come on the overall, how the deflection, etc. We try and see any other global structural engineer, global analysis, or who taking care of both the structures together. We'll try to arrange a topic with.
I'll give you the contact of the Bob that was responsible for WSP. So maybe we can have a separate session for that.
That'll be very interesting, Giovanni. Yeah.
Thank you.
Mr. Thank you. Mr. Abdullah is there? Abdullah, yes. Yeah.
Yes, I'm here.
Yeah, Abdullah is our honorary secretary, the man behind the technology with our all the CPD talks. Thank you, Mr. Abdullah. Thank you, all the committee. Thank you, Giovanni. Yeah.
Thank you.
Bye.
Thank
Good
you.
night.
Bye. Bye. Good night too.